All right, Charles. So what did we learn in this extended unit on convergence related stuff?
Well, I think the first thing we learned was convergence. Convergence is a thing, and it's something that we would like to be able to prove about our algorithms, and we can, in fact, prove them about some of our algorithms.
Like what?
That, for example, Q-learning actually converges. It doesn't just converge to something, it converges to Q star.
Oh yeah, that's pretty good. Now we did that in the form of a generalized theorem that broke the Q-learning rule down into actually kind of two little sub-update rules. And the proof basically says, well, if both of the sub-update rules do the right thing, then the overall update rule does the right thing. And that got us that Q-learning converges. And as you said, not just converges, but converges to the optimal Q function for the corresponding MDP, which actually is pretty amazing when you think about it, right? We have all these algorithms for solving MDPs, and Q-learning is like one line of code that just says, whenever you make a transition, do a little update like this. And nonetheless, this actually that actually works. That in the limit, it computes Q star. It's almost too simple not to try Q-learning.
Right. I mean, but hey, it's generally the case that simplicity is often the right thing to do. We call that elegance.
Ooh, nicely said.
So what else did we learn? Okay, so I learned some other words like non-expansive.
Or even better, contraction.
I do not like that word.
Really? It makes you uncomfortable?
Okay, so the last thing that I remember us talking about is speaking of generalized MDPs.
Right. And generalized MDPs have this nice structure that as long as the operators that are inside of it that are doing updates are not expansions, then we get these other kinds of convergence. We get the convergence of value iteration, we get the convergence of Q-learning. So we can actually combine these generalized MDPs with the generalized convergence theorem, and kaboom.
Yeah, and that's actually pretty cool because it would allow us to think about different kinds of decision processes, different sort of situations we wanted to be in, and we would know that all the math would go through, and so we could just do it. All we have to do is worry about whether they're non-expansive or not.
Right, exactly. And there's a whole set of things that we've shown are non-expansions. Oh, maybe that's even worth remembering. What are some things that are non-expansions?
Max,
That's a good one.
min,
More generally, order statistics.
yes, order statistics.
Fixed convex combinations.
Mm-hmm. That's my favorite.
Actually, I think all the things are kind of variations of those too.
Yeah, I think so.
You can get fixed convex combinations of order statistics, so we can actually combine those two things together.
Oh, that's cool. Is there anything else? I think that's all that we covered. Yeah.
Cool.
But I think importantly, you said something that I think was important, which was that not just any convex combinations, but it has to be fixed. That if the value of it can change, like with the Boltzmann exploration, then you do not know that it will converge.
That's right. Yeah, and it's actually kind of maybe an interesting open problem. It is definitely the case that we can prove that Boltzmann updates are not non-expansions. They can be expansions. But that's not quite the same as saying that therefore it doesn't converge. And there are some examples of Q-learning like update rules that have update rules that are not non-expansions, and yet it converges anyway. There's one that I was involved with really recently that we called Coco Q-learning,
Of course you
which
did.
is a two-player game setup. And that one you can show that it's not a non-expansion, but it converges anyway. Shoo.
Oh, okay. So look, one last thing, and I think we've covered everything, but one last thing, I realized we have an open question.
Okay.
So up on the very first line, you have convergence. And it's not just convergence for Q-learning, but the Q-learning actually converges to Q star, which is mildly miraculous. So are all these other things that we were looking at, these generalized operators and the order statistics stuff, those things converge, but do we know what they converge to?
Right. Yeah, they converge to that which they converge to. So in general, it's
Hmm.
not Q star, right? Because we're actually defining a different set of Bellman equations. So it actually is defining a different fixed point. Um, in some cases, those fixed points have good names. In some cases, not so much.
But do they converge to something that looks like the corresponding Q star? If you know what I mean? Do you know what I mean?
Yeah. So the idea is that they'd converge to something that makes sense with regard to how the Q equation is defined. So for example, if we replace the max in the action selection with some fixed probability distribution over actions, that's kind of equivalent, or maybe even is exactly equivalent, to having a fixed stochastic policy. And what we get convergence to in that case is the value of that policy.
Okay. So that's good. That's a big win. All right. So did I forget anything?
No, these are the things that I think were the critical high points of this fairly formal section, right? We did a fair amount of proving of stuff. I think we're going to do a little more of that before we get into some more implementation and practical stuff.
Okay, cool. So then you'll be doing those.
Yes.
That's great. Well, then I look forward to next time.
Awesome. All right. Thanks, Charles.
All right. Bye.